Do you know that Charles Augustine de Coulomb's discovered Coulomb's law in 1785? Now, what does it say? It says that it states that the magnitude of electrostatic force of attraction between like charges or attraction between like charges and repulsion is what? Between what? Between two charges is directly now from this law, it said it's directly proportional to what? Proportional to the product of what? Magnitude of 2-point charges. 2-point charges, and inversely proportional, or as inversely as, let me put it that way, and inversely as the square of what? Of distance apart. Now, this is the law that the man stated in 1785. He stated this law, and what he was saying emphatically was that the force of attraction or repulsion between two charges is directly proportional to the product of the what? Magnitude of the 2-point charges, and inversely as the square of what? Distances apart. That means the square of their distance apart. Now, mathematically, what we are trying to say is F is directly proportional to what? Q1 and Q2. F in magnitude, and inversely proportional to what? The square of what? Let's say R is the square, is the distance rather, square of distance apart. So where Q1 and Q2 now represent the what? The force. Represent the charge. Q1 and what? Q2 represent what? The point charges. Represent the point what? Charges. The magnitude of the point charges. Now, where what? Your D or your R, in this case we are using R, represent the distance between what? The two charges. That is to say, if I have what? This is the first charge, Q1. I have second charge, Q2. Now, the Q1 and Q2 are separated by a distance of what? R. By a distance of R. The radius, the charges are assumed spherical. So, although the radius of the sphere of the charge is negligible compared to what? Far smaller than the distance apart. That's why what? The radius of the sphere itself is not considered. Rather, we consider the distance from the what? The two charges, 2-point charges. Now, if what? They are like charges, for example, positive and positive, then what? It will repel in the direction of the line joining the two charges. But if they are what? Maybe negative and what? And positive, and positive. Let me use that, negative and positive, or like charges, and separated by a distance apart, which is R. Now what happens is that they will not attract in the direction of the what? Of the line joining them. So this one is F, this one will be F. If this one is F, this one will be F. It means that they still obey Newton's third law of motion. They obey Newton's third law of motion. For every action, there is equal and opposite reaction. So that means the force here that this we use to repair will be the same force that this one will use to repair. Don't forget, these are like charges, and why this one is what? Unlike what charges. But the force of attraction or repulsion, the magnitude of the force of attraction or repulsion between the two charges is directly proportional to the product and inverse proportional to what? The square of what? Of the distances apart. Now, of their distance apart. Now, that's what this law is saying. Now, there's something I want to bring out from here. Now, if you remove the proportionality, what do you have? I want to have K in what? Q1, Q2 divided by what? R square. Now, before I go further, don't forget there are three things that the electric force or electrostatic force of attraction is talking about here. Now, number one is that, take note, that it what? It depends, electrostatic force here, static force depends on what? On one, the distance between the charges, distance between the charges, between the charges. Number two, it depends on the what? The material medium, the nature of what? Of the medium between the charges, between the charges. And lastly, it depends on the what? The charges. Depends on what? The charges. Depend on what? Depends on the what? The two charges, 2-point charges. 2-point charges what? So there are what? Three factors upon which the force depends on. It depends on the what? The 2-point charges, Q1 and Q2, Q1 and Q2, Q1 and Q2. It depends on the distance of what? Of separation, that is the distance apart. And lastly, it depends on the medium upon which what? The nature of the medium between the charges, the two charges. Now, these are the three factors. Now, this K that I just introduced now is as a result of what? Removing the word, the proportionality. So it's called, we can call it the Coulomb constant. Coulomb what? Constant. Constant. Now, one thing you must know, actually, the first law that Coulomb's explained was that like charges repel, while unlike charges what? Attract. So there are two nature of forces that exist here. The nature, the attractive force and repulsive force. There are two nature of forces that coexist in this what? Electric field or magnetic electrostatic force. Is that there are what? Attractive force and what? And repulsive force. And these forces are what? Are acting along the line joining the two what? Charges. Now, another thing again you must know is that the force that is acting on Q1 is equal to the force acting on Q2. It's just that they act in the opposite direction, obeying Newton's third law of motion. Now, when you remove the word, the proportionality, you introduce K. Now, our K is actually what? Because I say to believe me that, okay, it also depends on the medium, is equal to 1/4 pi epsilon. Epsilon. This one is called what? What? The permittivity of the medium, between the two charges. That is what we call what? That is the permittivity between the two what? Between the two charges. The permittivity of the medium between the two charges. That is epsilon. And don't forget that that's why we say it depends. If you put it here, you are going to have something like this. F magnitude is equal to what? We would have 1 over 4 pi epsilon Q1 Q2 over what? R square. Now that is what? The formula. But this formula now we can reduce actually, because epsilon is the same thing as what? That means permittivity of the medium is the product of what? Relative permittivity and permittivity in free space. So this one now is called what? Relative. It's called relative what? Permittivity. Why this one? Now, this formula, I'm still going to talk about it, but take note. Then, this one is what? Permittivity in free space. Free space. Now, this one does not have a unit, this relative permittivity. We can also call it the dielectric constant. Most of the times, they are what? Most of the natures that have this material is what? Are insulating materials. Most of them are insulating material. Most. Now, another thing again is that the relative permittivity of air, for example, is equal to 1. Don't forget, the relative permittivity, epsilon R of air, equal to 1. So that's why epsilon is equal to what? Epsilon naught in air. Since epsilon R is equal to what? 1. Epsilon R is equal to 1. So epsilon is equal to what? Epsilon naught. Now, as I was saying, I have to clear this part. Now, let's go on with the course. Now, as I was saying, that in air, epsilon R equals to epsilon R equals to what? 1. And if you put 1 here, epsilon will not be equal to epsilon naught, and which is permittivity in both in free space or in vacuum. Now, don't forget that epsilon naught is what? 8.85 times 10 raised to the power minus 12 Newton what? Don't forget, this particular one, if you make F the subject of formula, that means you are going to have what? Coulomb square per meter per Newton, per meter square per Newton. That means if you make what? Epsilon the subject of formula, this one and this one will have the same unit. This one also have a unit of what? Of Coulomb square per Newton per meter square. So that is the unit of what? Or farad per meter. Farad per meter. That is the unit of what? You can write as farad per meter. Any of the two is correct. Now, as I was saying, you remember that, okay, let us substitute this formula into this one. Let's put it here. What do we have? We are going to have what? K equal to what? 1 over 4 pi epsilon R epsilon naught. That means we are going to substitute this particular formula inside this particular one for what? Epsilon. So this is what we are going to have. And don't forget, this one I said as what? 1 over 4 pi epsilon naught epsilon R. Similarly, now K naught is equal to 1 over 4 pi epsilon naught. So K naught is equal to this. And if that is your K naught, this formula can be broken down to what? K equal to what? Then you now replace this one with what? Now be what? Do you know you can write this one as this times what? You can write this one as 1 over 4 pi epsilon naught times 1 over epsilon R. This one is same thing as this. so that we can see our K here. This is K naught. So we can now say K naught times 1 over epsilon r. That will now be K equal to what? K naught over epsilon r. But what is our K? If you put the value of pi, take your pi to be 3.142 or 22/7. Take your epsilon of permittivity in free space, which is a constant value, as this value, put it here. You are going to have approximately 8.99 times 10 raised to power 9. In most calculation, we use it as what? As 9 times 10 raised to power what? 9 Newton what? Meter square per what? Kilogram. That's what we use it as. So that is the unit of that K. Newton meter square per kilogram. That is the unit of that particular K. So in that case, we don't use at 8.99, rather we use approximately 9 to subtract. So you see in question, take K to be 9 times 10 power 9. So this is it. The relationship between K and what? K naught. This K is constant, column constant in a medium. This is column constant in free space. So epsilon r equal to what? Column constant in what? In free space divided by column constant in what? In medium is K, ordinary K. Now we have done that. Let us now work with what we have. So in medium now, in medium we can now say F is equal to K. Instead of writing this one now, this one as one like this now, you can now reduce it to what? Remember that this one is same thing as what? Q1, Q2, or divide by what? 4 pi epsilon naught epsilon r square. So instead of writing it that way, you can actually write it as K naught over epsilon r, then times r square. Then we now have what? Q1, then Q2. That is the formula. This one is in what? In medium. In medium. Don't forget. When it is in medium, this is the formula to use. Now, that means that K naught is what? Our value. This is what? Relative permittivity. They will give you a dielectric constant. Epsilon r is relative permittivity. Then our r is what? R square. Now, another thing again you must have at the back of, or you must know, is that for a medium, each of the said identical charges, I'm still talking about a medium now, if they said identical charges, identical charges, what do you mean by identical charges? Identical or similar charges or equal charges. That means Q1 and Q2 are equal. That is what I'm saying now, is Q1 and Q2 are equal to Q. Now Q1 is equal to Q2 and it is equal to Q. What will now be our what? Our formula for the what in the medium? What will be our formula in the medium? Now the formula will now be what? Reduce this one too will now be reduced to what? F magnitude, which is magnitude of, that's why they are taking absolute of charges, because you are finding magnitude, will now be K naught, then will now be what? Q square. Now why is it Q square? Put Q here, put Q here. Q times Q equals Q square. All divided epsilon r times r square. So this is also in a medium. A medium of what? Of two what? Equal charges. But what about in air? What about in air? What about in air? Now, in air, the epsilon r equal to 1 in air or in free space. When the two charges are placed in air or in free space. Now, what happens is that epsilon r will now be equal to what? 1. So our formula will now be F is equal to what? Now be equal to K naught Q1 Q2 divided by what? r squared. This is what in air or in free space. But what about if the two charges, if Q1 is equal to Q2, what about all equal to Q? What will now happen? Just like the way we have equal charges or identical charges. When we have equal charges, like the first case that we just did for medium. Now what you are going to do is to just substitute what Q for Q1 and substitute Q for what Q2, which the formula will now be reduced to something like this. K naught now be Q what square all divided by R square. So don't forget R must be measured in meter. Q is in what? In columns. Q1 and Q2 in columns and force is in Newton. Don't forget that. So it's in Newton. So that is what we are going to have. Then if you want to now make your, for this one, if you want to make for, let's say this one is what? In air of equal what? Charges. Now for the two of them, you can actually make your Q a subject of formula. For in air and in a medium. So if you want to now make what? Your, if you want to make in a medium now, you want to make Q the subject of formula, I can say Q square is equals to, that means equals multiply KQ square, K naught Q square, that means let's say over 1 times K naught Q square, we have K naught Q square, then F magnitude times what? Epsilon R times R square. Divide both sides by K naught. So if you divide both sides by K naught, so where's what I want to have first? This all cancel. So Q will now be equal to what? If you take square root of both sides now, this is what we are going to have now. Absolute of force times R square times epsilon R divided by K. So how do you remove the square here? Take square root of what? Of both sides. So when you do that, your Q will now be equal to what? Square root of what? Absolute of what? Of force magnitude times what? Times the epsilon R times R square divided by what? By K naught. Now, I haven't done that now. You can also do that of what? That one is in what? The charges in what? In a medium. What about in what? In air. How will that one reduce to what? It will now become what? Because this one will now be 1. So it will now be what? Absolute of force times R square divided by what? By K. So that will not be our, why we are taking absolute, because if they give you negative force, maybe minus 40, you can also turn it to plus. Because we are taking only the magnitude, we are considering magnitude. This one is in what? In air. To calculate charge in air. That is what that one is talking about. Is K naught. So that is, and don't forget your K naught is what still remain what? Approximately what? 9.0 times 10 raised to power 9 what? Newton meter square per column square. So that is what? Your unit. Now, having understand that now, having clear all your doubts concerning that. Now, what again? What about other ways? If it's vector, there's a question they will give us, they will have a direction. Because don't forget, force is a vector. So in as much we believe that force is a vector, we can represent it vectorially. We can represent a force vectorially. So the unit vector of radius of a displacement, normally unit vector is equal to the vector over the magnitude. So the vector, this R is this what distance between them. So the vector form of R is equal to unit vector. So R, this was a unit vector of what? Of distances, or in this case we can be called displacement or the position. Unit vector of the position. So this is a vector over the what? Magnitude. Now, let us what? Write it in terms of what? Unit vector. Now, what will happen is that we are now going to what? Put this one, I mean, the force now be equal to what? We no need to put magnitude again. Now be what? Q1, Q2 over what? Over R square. Now put. Now, why are we putting this one? Remove. No, we have removed the absolute. This absolute, what does it do? This absolute so helps to remove minus from the two charges to now be in terms of plus. For example, if I give minus 2 microcoulomb, by the time I take absolute of this one, it will remove the minus sign. I'm not saying bracket. It will eliminate the minus. Absolute will help us to eliminate the minus sign. Now becomes what? 2 microcoulomb. So it kills the negative sign naturally. So that is what absolute this thing does. Now, this particular one, so if we once we put unit vector is to determine direction. Unit vector of what? In the what? In the direction of, or let me call it unit vector in the direction of what? In the direction of R. So this one now, we are in the direction of R. So this is a unit vector in the direction of R. So if we want to now find unit vector, I mean the vector in terms of, this is vector form of representing what? Representing electrostatic force. Because I know some of us are writing professional exam. You now see something like this, they not absolute. You now begin to get worried and all that. Another way you can write this formula that I just give you now is into doing put what? The vector divided by radius for this particular unit vector. So it now becomes F equal to what? K naught Q1 Q2 over R squared. Then R vector, that is R, divided by what? R. This one is unit vector. This one is vector. They are different, This one indicates magnitude and direction. Or we can write it as that means bold R. You can write it as bold R. This one is what? Not light R with arrow. This one is unit vector that indicates direction and has a magnitude of 1 of unity. This one indicates both magnitude and direction of that particular word, vector R. So in that case now, they are two different things. So if I put vector here, not unit vector, if I put vector here, I will have to divide by R using the word. That means in place of unit vector, I substitute all this one there. The formula becomes what? Many of you have seen this kind of formula before. Q1, Q2, then R vector divided by R cube. We have not seen it before. It's still correct. This is still correct because this is Coulomb'S law. This is law of electrostatics. So this is correct. So you see it this way. You see it F equal to what? K naught Q1 Q2 R vector over R cube is correct. So take note of this, take note of this, take note of all the forces I've given to you and how to look for it. Now don't forget that it was even Coulomb'S that also say that like charges repel while like charges attract. In some textbook they will tell you it's what? First law of what? Coulomb'S. Second law is what? It's saying that the force, the electric force, electrostatic force is what? Directly proportional to the product of the charges, of the magnitude of the charges, and inversely proportional to what? To the square of distance apart. We can also say that represent inverse square law. So it's explained that force is inversely proportional to R. Now, another thing again, I will have to chip in here. Please, you pardon me to chip this in. Very important. If you check, I say F is inversely proportional to square of distance apart. Now, it means that when you remove proportionality, you then have what? Let's introduce any constant. Let's say P over R squared. Now, cross multiply, you have what? P is equal to what? FR squared. Now, let's create a case where the forces, they are given two different forces, and with two different distances in the case of R1, R2. Now, we are going to have it as F1, R1 squared, F2, R2 squared. So that's what we are going to have. F1 R1 squared equal to F2 R2 squared. That means you keep charges constant. What is our charge here? Our P is constant K, and what? Let's say in air, then Q1 and Q2 are also kept what? Constant for the two charges. You only vary the what? The force and the distance. For instance, look at what I'm saying. They will say, okay, if the distance between the what? Q1 and Q2 is what? Let's say is 5 meters, and the force of attraction between the two unlike charges is what? Let's say 10. They will say if the distance is doubled, what will be the force? That means they are keeping the what? The charges constant, and what? They only vary the distance and the force of attraction or repulsion that coexist in that particular word of field, electrostatic field. Now, in that case, you must ensure that the charges are not moving. They are statics. They are static charges. And we must also ensure that these charges are spherical. They are spherical. Number two is that the radius of these charges are smaller. They are negligible. They are smaller compared to the distance apart. So since the distance apart is far greater than the what? The radius of the sphere that we are talking about. It means that what? We consider the radius of the sphere as distance apart. Another thing is that, strictly speaking, this theorem of Coulomb's law is only what? Focusing on point charges in a vacuum or in free space. Strictly what? Fundamental that you know, although it can be applied to a material like homogeneous or isotropic what? Dielectric system like medium. But basically, fundamentally, strictly speaking, that what the Coulomb's law itself is applicable to point charges separated by a distance of r in a free space. That is their basic and fundamental theory, what it applies to. So it can also apply to the cases of in a medium of isotropic medium and so homogeneous medium, as the case may be. Now, these are what the basic thing you must understand and you must not forget about what Coulomb's law. Now, what I'm going to do in my next class is that I will look at one or two questions that will ensure the backup of this particular class, that will ensure that we understand everything I've done in this class will be backed up by those questions. And don't forget to, in our previous classes before this class, you remember that this formula I've given to you, that means Q equal to what? If I want to just take only the force, the magnitude of the charge is equal to magnitude of force times r squared over k naught. This formula I gave you here now. Don't forget, they can ask you to find the number of electrons, because remember that Q equal to Ne when we are talking about the principle of quantization in the part 1 of this class. We talked about what principle of quantization, and I told you Q equal to what? N, where N can be 0 plus or minus 1 plus or minus 2. And I told you quarks are exemption. Go and watch. They are exempted from the principle of quantization. So this formula can be related to that. It can also even be related to what? The number of mole. It can be related to what? Number of mole times what? Avogadro's number times Z, proton number times electron. I give you, go and watch it. Also, what can also be related to IT, current times time. I gave you that. It can also be, sorry for that, please. It can also be related to what? Mass over molar mass times Avogadro's number. Mass over molar mass times Avogadro's number times what? Proton number. Remember that number of moles is equal to what? Mass over molar mass from the basic knowledge of chemistry. So proton times what? Times electronic charge. Don't forget electronic charge we have talked about. You go and watch all this. So all this charge in a case of identical or equal charges can be equal to NE. Because the other time they can tell us to find the number of charge that the body or the object is carrying. So these are the basic things we need to know about Coulomb's law. And this man, Charles Augustine, the Coulomb's actually talked about this particular theorem that we are talking about, this law that we are talking about. And don't forget, charges are measured in what? As measured in coulombs. They are not measured. And to define coulombs, you have to do that for me in the comment section. What is coulombs for a what? A unit what? Charge. What is it defined as? Right? Tell me the definition of Coulomb's law of according to what? This man. And send the answer to the comment section. Thank you very much for watching and have a wonderful time or wonderful day with yourself. And please ensure you click the like button and subscribe to this channel to always encourage us to come on this platform to post videos and classes that will be a blessing to every one of us. Thank you. God bless you.